Hello, my name is David Foster, and I wanted to share some of my insights, my conjectures regarding divergent series and what conclusions I've come to about them. Now, okay, a little small caveat. I'm not a pure mathematician. This isn't fully rigorous yet. It's getting there. I'm a physicist, which means I take a very different attitude. Mathematicians like to build their tools deductively from the very ground. If I want a tool, I go to Home Depot or Harbor Freight or something. You know what? I get tools to use them, not because I want to invent the screwdriver again. Um, but this all really started with, of course, Numberphile's infamous video on the sum of the integers equaling -1/12. I saw a lot of mathematicians just to try to explain it away. They'd say, "Oh, it's not a sum, but it's not a sum in the usual sense," but then they wouldn't really explain what it is. These do have real-world significance, and so it's important we understand them physically. Or a comparison, look at how a mathematician defines a vector compared to a physicist. They'll say it's an arrow. Or a computer scientist, it's an array. Because these have real-world uses, and so we use them. So we need more than just analytical derivation. Here's a couple examples. Of course, you got the enigmatic zeta function and its various cousins, such as the eta function. We have these other miscellaneous series. I could go on here. That's not my point right now. I want to investigate a couple of them from a unique standpoint. It recently come to my attention that at least one gentleman figured this out, or used a similar method on Grandi's series about 1830. But I haven't heard too much more since then. So let me show you what I'm doing here. Let's start with a 1/2 x plus 1 equals y. Very linear equation, nothing too spectacular. Now, I want to investigate the fixed point of this equation. The fixed point is the point where if we take a function, we set it equal to whatever value we put in. So if we have f of x, the fixed point is where f of x equals x. Okay, so in other words, it'll always lie along the x equals y line, because you're basically saying x equals y. Okay, so for our function right here, this 1/2 x plus 1 equals y, the fixed point would be 1/2 x plus 1 equals x. The solution to that is the fixed point. We can see it on this graph because it's where the two lines cross. Real complicated. Now, what if we start at 0? If we start at 0, we can go up 1. Well, let's go back over to the, we can do this by iteratively nesting iterating these functions. I'll show you what I mean by iterating in just a minute. But it leads to a progressive series of 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 and so forth. That line converges to the fixed point. So we can say that 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 is equal to that point. And that point happens to be 2. Because that's where, if x equals 2, then 1/2 x plus 1 equals itself. X equals 2. And first, for reference, this is an attractive fixed point. It's not the only kind of fixed point, or the only kind we're going to see. But this is a convergent series. This isn't controversial. This is convergent series are the workhorses of math. We use these all the time. But let's take a quick, before we go on, let's take a quick look at the equation we used. Now, I started off with 1 equals 1/2 x equals y. Now, let's just say that first set one side of the equation equal to x. So 1 plus 1/2 x equals x. Now, we already know what x is. X is 1 plus 1/2 x. So let's nest it inside of itself. Let's do that again. Let's do it again and again, and infinity ad nauseum. What does that give us? Well, we get 1 plus 1 half parentheses, 1 plus 1 half parentheses, and so forth, equals x. Notice that the x is now buried in the ellipsis somewhere. You can't even see it. I like to call that a Ponzi function because, like a Ponzi scheme, you put off paying everybody until, well, you're making money. The whole Bernie Madoff thing. Okay, so let's simplify this. I can simplify the first parentheses, get 1 plus 1 half. Now I have 1 half times 1 half times 1 plus 1 half, so parenthesis, parenthesis, parenthesis. I can reduce this further to simply say 1 plus 1 half plus 1 fourth plus 1 eighth plus 1 16th plus 1 32nd. And if I can go back to what I had just done. If I had plugged 0 into there, I could have iteratively gotten there. That's right. I could have plugged 0 into 1 plus 1 half x equals x, and iteratively gotten the solution. This is what this is, plugging it into there over and over. But the main point here I wanted to make was that these equations in red are all the same thing. Or I can write this out a little more clearly. We get 1 plus 1 half plus 1 fourth plus 1 eighth plus 1 16th and so forth. Well, as we go on, we get higher and higher, smaller and smaller fractions, and a smaller and smaller x term equals x. So as we take a limit, which is the standard thing to do, what we really get is a horizontal line. And we're left with the conclusion that 1 plus 1 half plus 1 fourth plus 1 eighth plus 1 16th is equal to 2. The solution of the function never changes because we're always replacing x with what x equals. Now, this is a graphical example of what we just discussed. Now let's investigate this. Very different. Now we have this is not an attractive fixed point. Here, let's zoom in on that a little bit. Here, if I plug 0 into this and iteratively solve it, I get 1 plus 2 plus 4 plus 8 plus 16, and so forth. Now, most people would say, well, this obviously doesn't converge to anything. Yet, there are summation methods where we can assign it a perfectly finite value. Furthermore, okay, by the way, this is a repulsive fixed point here. I should point that out. And as we iterate this, we get a progressively steeper line until we have a perfectly vertical line. And once again, we can iterate the functions, nest them inside each other. And as we do that infinitely, we can get 1 plus 2 plus 4 plus 8 up as high as we like, and a higher, larger and larger value of x. But again, okay, let me back up a little bit. We have powers of 2 here. Okay, look at the second red one, and then over to the equation I have it equal to. Okay, this the second red one. 1 plus 2 parenthesis, 1 plus 2 parenthesis. At every point, this equals the original value. Because we always say x equal to what x is equal to. We just did it a whole bunch of times. Now, if we multiply that out, we get 1 plus 2 plus 4 plus 8, up to 2 to the power of n plus 2n plus 1x equals x. But you don't see that middle x term, that 2 to the n plus 1 equals x. If we do it infinitely, it becomes buried. I'd like to make a point that these divergent series are their own mathematical structure. Every bit is unique and real in the parentheses, as the imaginary numbers. Nonsensical looking, absolutely. Yet they have real uses, like the imaginary numbers, and they're important. They're a real mathematical structure with their own rules. And so, yeah, using these summation methods I mentioned, we can come to the conclusion that 1 plus 2 plus 4 plus 8 plus 16, and so forth, is equal to minus 1. Now, see, that boggles my mind, which is what got me fascinated with this to begin with, that we are assigning a finite value for what shouldn't have. Well, I mean, you look at this, it looks like it should equal infinity. And yet we know from physical real-world experiments that we do get finite values. Now, I would say it's better to say that instead of saying we have a sum, I'd say it's better to say we have a solution. In other words, the solution to these nested functions is negative 1. We could say it's the sum, and it kind of looks like a sum. It's not a sum. It doesn't have the same rules as a sum. If you had a finite number of terms, if we just added just up to 8 or 16 and stopped there, then all the ordinary rules of addition we know we could use. But when we have an infinite number, we can't. We cannot do that. And yeah, Mathologer has a great video on the Riemann rearrangement theorem and the things you can do. I might link that later or put it in the endnotes. Okay, in that case, the solution, what we have here is the solution to a function, and that function, infinitely iterated, is basically the series representation. Now, is this only series? No, not at all. We can do this. This is equally applicable to continued fractions, nested radicals, towers of powers. Ramanujan's famous, what was it? Root of 1 plus root of 2 plus something, whatever that it was. It's pretty much the method he used. Let's take one more example here before we go. Grandi series. I'm going to start with the equation 1 minus x equals y. If we start at 0 and iterate that, we get 1 minus 1 plus 1 minus 1 plus 1 minus 1. And it just continues on like that. It doesn't go away from the fixed point, it doesn't go approach the fixed point. But the fixed point's right there. If we iterate these functions, we can get, as I said, 1 minus 1 plus 1 minus 1 plus 1 minus 1. Famous old series. People argued about this for a long time. But if we do it graphically, like this, we can see that we're basically orbiting the fixed point, not approaching it or going away from it, but just approaching it. Now, this is useful. This is basically a lot of the same behavior we see when we look at the logistic map, the logistic equation. We can write the map as n subscript n plus x to the n subscript n minus plus 1. Excuse me, I might stutter. Equals r xn 1 minus xn, where x and x subscript n and n x subscript n plus 1 are just successive values of n. Logistic equation, we could talk about this all day. This is a very important topic, and it's basically doing a very similar thing, but with much more complex behavior. Okay, so that's what I wanted to talk about. I think we have some very useful things here and a useful framework and a useful way of looking at this. I think that these divergent series do have real-world uses and real-world meaning. That it's not just analytic, it's not just something we get from analysis, not just some math theorems. This is real. Thank you, gentlemen, and I look forward to talking to you in the future.